Overview of the electrical side of the science. We're going to be covering Learning Outcome 2 this half of the year. It's to investigate and apply direct current and alternating current theory to electrical circuits. The assessment is the same as the mechanical half. You're going to do a practical investigation and lab report worth 20% of your overall mark for the module. And an examination of 1 hour worth 30% of your overall mark for the module. So you're halfway there at the moment, having taken the mechanical half. You're now going to work on the other 50% for the electrical half of this module. So that's where we're starting today. So what we're going to be doing this morning is pretty much revision of stuff that you hopefully would have already done either in a BTEC or physics at school or some other course where at a lower level than this, level 3, level 2. Basics of electricity, really, Ohm's law, power, that type of thing. So first key quantity with electricity is voltage. It's the pressure applied to a circuit, and it's what pushes the current around. You can think of it like a high tank of water, and if we open the tap, the water will flow down to the lower level. It's the pressure or the force, the potential for current to flow. Measured in volts, okay. Also has different names. Potential difference. Difference in voltage between 2 points. So you can have a point in a circuit that is at plus 12 volts and another point in a circuit that is plus 6 volts. There's 6 volts potential difference between them. Current will flow between them. Electromotive force. That's a term used when we're considering the voltage coming from things like generators. Okay, so there's lots of different terms you'll come across, all measured in volts. The key point here is that current flows in a circuit or a component because of a difference in applied voltage. So if 2 points are at the same voltage, it's like having 2 tanks at the same level, no water flows between them. So if you've got 2 points in the circuit, both at 12 volts, no current will flow between those 2 points. They are at the same potential. Okay? And one key thing here, and I will pick up on anyone who says it, voltage doesn't go through anything. Current goes through, voltage is measured across. So if somebody says to me, there's 12 volts going through that circuit, I will definitely tell them they're wrong. Okay? Because volts don't go through. Amps or current goes through. Current, second quantity. Current is a measure of the rate at which charge is flowing in a circuit. Designated by the symbol I. So we use I to designate a particular current, and it's measured in amperes, or amps for short. We use a symbol A for that. It's a capital letter A, and it's a capital letter I in those cases. Sorry?
It's imaginary I.
No, it's not that I, Paul. Alright?
Right.
Yeah. The imaginary I is what mathematicians use for the imaginary part. We use J.
Oh, yeah.
Okay? Yeah. Sorry for the confusion, but
No.
I didn't invent the system. So amperes, amps, measure is the measure of current. It's how much charge is flowing past a point. Resistance. So this is the resistor in this circuit here, and the resistance of an electrical circuit is a measure of what the opposition or restriction to current flow. How much opposition there is to current flow in a circuit. designated by the symbol R, so we put R there for resistance, and it's measured in ohms. We use the Greek symbol capital omega for that. Okay, so we would label this up like this. There's the current I, measured in amps, it's flowing through. We use an arrow to show its direction. Okay, later on we will come across the use of the lowercase I, the lowercase v, and that's when we're talking about instantaneous values. When we talk about uppercase, we're talking about the maximum value flowing. More about that later. And then here we would say we've got a potential difference or a voltage, and for a source we often use E measured in volts for EMF, because that's a source. Okay, but we can also talk, we'll be talking later about volt drops or potential differences across the components around the circuit as well. When current flows through a resistance in its most basic form, electrical energy is converted to some other form of energy, such as heat, light, or rotation of a motor. So without any resistance, we wouldn't do any work. We wouldn't generate any, we wouldn't use any power, we wouldn't do anything useful with that electricity. So a circuit has to have all of those components, and then to be complete it needs some kind of switch so you can turn it on and off, and then you've got your most basic circuit. All parts of a real circuit have some resistance to flow, and without it there'd be no conversion of or use of electrical energy into another form. Everybody all happy with this so far? Yep. Power. So this, when we start to use energy, we use power. Power is a measure at the rate of which energy, measured in joules, is used. In electrical terms, it's the rate at which electrical energy is converted to some other form. Power has the symbol P and is measured in watts, symbol W. The power is dissipated in a component or circuit resistance can be found using the following formula. The current times the voltage. There are two other ways in which you can calculate power. Anyone remember them? Anyone know them? Who's been on the BTEC here? I squared R, so we can do P is equal to I squared times R. And the other one involves V and R. P is equal to V squared divided by R. These can all go with Ohm's law. I is equal to V over R. If we know those four formulae, and they are the four most basic formulae in electrical engineering, and they follow through all levels of your learning on this course, right up to level 6. If you can get Ohm's law, it gets more complicated as the circuits and the components get more complicated, but it's still those, the formula is still Ohm's law and the three power formulas. Okay. Once you know those four, if you're given any two values in the circuit, the current, any two of the current, voltage, power and resistance, you can find the other two using the combination of those three formulae. And we'll be doing some work on that in the tutorial session later in your smaller groups. Okay. So everyone happy with that so far? So if we have an example problem, 75 volts is applied to a resistor, and the current flowing is measured to be 15 amps. Find the value of that resistor. .75-volt source, an unknown resistor, R. We measured the current, and that's 15 amps, and we'll also find the power. Which version of that formula would you use to find, which formula would you use to find the resistance?
Voltage over current.
R is V over I, yeah, voltage divided by current. 75 divided by 15 is, sorry, 5, yeah. Always put the units, you'll lose marks in the exam if you miss the units off. Not many people did this year, I noticed in the exams that I looked at, but must include the units. And then the power, which formula would you use for the power? Yeah, I would use IV here. Which is 15 times 75 equals
Uh,
750. 1125 watts. Yeah. When you do calculations like that, and you've got a range of different formulas you can use, always try and aim to use the values you've been given if you can. And in this case, this worked out exact, but in most calculations you do it won't, and you'll round that figure. If you don't have to use that figure in the next calculation, if you can use one you've been given, then do so. Always use given values if you can for most accuracy. Yeah. So there are other ways we could calculate that, and in this case we get it exactly right because that is exactly 5 ohms. But if we'd have rounded that figure and then used it with compounding errors, I'm sure Mark talked to you about that in semester 1. Okay. Everybody happy with that? We move on. Yeah. Example problem 2. Find the voltage required to be applied to a circuit of resistance 16 ohms to make a current of 1.5 amps flow through the circuit. Also calculate the power dissipated. I'll give you about 3 or 4 minutes to have a go at that one. So, how do we find V then? Yeah, current V equals I times R, 1.5 times 16 equals 24 volts. Yeah. And this is definitely the way to lay out your exam question answers. Write the formula down, put the numbers in, give me an answer, and underline it, because there are marks given for working. If you make a mistake with your calculator, push the wrong button or something, sometimes you can get some marks for the method being right. Okay? And I can see where your wrong figures come from. If you told me what you're supposed to be, you're going to multiply the current by the resistance, and I can see you used the wrong current or something, maybe. And then when if you get an answer wrong, but then you use the result late in a later question, you can't be penalised twice. I have to work out all the answers and see whether you got it right with the wrong figure in the first place, because you don't get penalised twice for the same mistake. Okay, so that's the way to do it. And then next part, power. Which version? Yeah, use I squared R because that uses the values that you've been given. So that's 1.5 squared times 16 equals 36 watts. Marcus, so it does. Alright, so that's the easy answers to that one. All fairly easy stuff so far. Yep. What's going on with this? Not having a good one. The issue here is submultiples and multiples is when you use them in formulae. So we're talking about, I don't know what's happening. Right. Multiples and submultiples. Often we get very large quantities like kilovolts, megavolts, gigawatts. Also very small quantities, particularly current and the so we get milliamps, microamps, and when we get into capacitance, microfarads and smaller. And so we use the engineering multiples and submultiples, giga and mega, 10 to the 6, 10 to the 9, and so on for those quantities. What you have to be careful of when you get those, a mixture of those in formulae, is that the ohms law will only work if all the quantities are in the same base. So amps, volts, and resistance. One way to deal with that is to use the multiples of 10 to deal with the fact that you've got volts and you've got milliamps. Okay? If all your quantities are in the same multiple, then you can just put the numbers in and the answer will be in that multiple as well. So if you've got millivolts, milliamps and milliohms, just put the numbers in the formula and your answer will be a multiple milli. But if they're different, then use the power of 10 notation carefully with your calculator. One thing you need to be careful of is if you're going to square a current that's got a 10 to the minus 3, you need to put the current in brackets and then square the brackets, otherwise you won't get the answer right out of your calculator. So just be aware of things like that. So if you've got 10 milliamps and you use 10 times 10 to the minus 3 and you're going to square that to get the power, you need to put the current in brackets and then square it, otherwise it won't give you the right answer. Okay, so we'll be having a look at some examples in part 2 of using those. But just be aware that that's needed because all your units must be in the same multiple. Okay. Now, moving on a little bit further, series resistance. So when we connect resistors end to end, like so, R1, R2 and R3, we say they're connected in series. And the current, we have one current flows through all of them, a bit more about that later. So the same current flows through a series combination of resistors. And you calculate the total, we call it usually RT, and we say that's R1 plus R2 plus R3, and we can carry on using that for Rn resistors. Any number, just add them all together. Again, we need to use the multiples and submultiple notation if appropriate. Okay? So series resistors, just add them up. And if you think about them, each of them is like a blockage in a pipe. If we got 2 blockages, we got twice as much blockage as what we would if we only had 1. So that makes sense. Yeah. And throughout this module, sure, Mark said the same thing. It's not just about the maths that you've got to do. There is maths in it, but it's important to understand the underlying principles involved here. More resistance, less current. More voltage, more current for the same resistance. That's how Ohm's law works. Okay? So underline electrical principles, get them in your head, and you can't, that helps you not to forget the formula then. Next bit, parallel resistance. When resistors are connected across each other, so if we have a circuit like this, and we could have any number of them, I'll make that one have 3, okay, those resistors are connected in parallel. They'll have the same voltage across each of them, but there'll be a different current flow through each resistor because it's got multiple paths. Okay? What do you think happens to the overall resistance of that circuit because there's 2 resistors? It's like the water's got 2 different ways to go. So there's overall less resistance, yeah, because it's got 2 different paths it can take. So the route from there to there, for instance, if that's the direction the current's got to go through, overall the route is easier. It's like having 2 roads to go to the same place. The traffic's got more space to spread out in. Okay. Now, there are 3 methods that we can use when calculating parallel resistance. I'm going to label these up like so. The first one is where there are only 2 resistors, but they can have any value, and that's called the product over sum rule. And it is that RT is equal to R1 times R2 over R1 plus R2. So if you've got just 2 resistors, it don't matter whether they're different values, you can use that method to find the total for that pair. So we could use that one on this circuit here. We couldn't use it on that one there because it's got more than 2 resistors in it.
You just leave it the same and just then add another times R3 at the top and then plus R3 at the top. If you can do it 3 or 4 or 5 or 6 or 7.
If you could do that on that circuit, because you could do a product over sum on that pair, and then take the result of that and do product over sum with the result in that one. That's a bit unwieldy. There's a better way to do it. Okay. If you've got 3 or more resistors, up to any number of resistors, and they're different, and this one works in fact with any number of resistors, you can do it with the 2, and that is that RT is equal to, we need a set of brackets, R1 to the minus 1 plus R2 to the minus 1 plus R3 to the minus 1 plus Rn to the minus 1. Close the brackets, all to the minus 1. And that one will work with any number, hundreds if you want. Okay? You may also have seen that one in this form. 1 over RT is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on. The reason I don't teach that way is because it causes students they tend to forget that it's the reciprocal of the total that equals them added together. So I prefer to get rid of that, and the modern calculator uses the x to the minus 1 button to achieve the reciprocal. So it just works better with your modern Casio calculators to use that method. Okay. Sometimes it's appropriate to remember that you can do it that way, but not that often. Alright? I'll leave that one on the bottom there for reference. Okay. Where you've got multiples, any number of resistors, and they're all the same value. So you've got, let's say, 4 of the same value resistor in parallel, but that can be any number, and they are all of value R. Okay, then RT is equal to that value R divided by how many there is. So if they were 400 ohm resistors, the total resistance there would be 25 ohms. And the one thing to remember, with there's a little bit of a check, is the total is always less than the smallest resistor in the combination. So if we've got, going back to our 3 resistor one here, if we had a 10 ohm, 100 ohm and 1000 ohm, we know the total is going to be less than 10. The total is always less than the smallest one. Parallel resistant combinations. Yep. There's something up with this file I got here this morning.
So where you just wrote RT equals R over N,
Yeah.
in here it's RP. So
Yeah.
P doesn't.
No, RP is the value of all the resistors in the parallel combination.
I see.
They're all the same. They got to all be hundreds or all thousands or all. Yeah. Where you got a combination, it's quite common to use that technique to make up a resistor value that you haven't got. If you want a 50, well, that's not a preferred value in resistors. But if you want a 50 ohm resistor, you get 200s and put them in parallel, because that cut the effectively halves. Yeah. Because 100 is your value. Well, 25 is not a preferred value either. Yeah. So, but 100 is a very common preferred value. So you can create a 25 by putting 4 of them in parallel. All right. Yeah. But they all have to be the same value to use that formula. Remember that the long one, the power to the -1, will always work with any combination and any values. Okay. Series and parallel combination. There's 2 different combinations that you can get. You can get, and this is a basic combination, and then you can get additions for these. First of all, combination type 1, where you've got a resistor in series with 2 other resistors in parallel. We don't have a formula for that in one go. Well, we could actually write one, okay, but we're not going to do that at this stage of the course. Later on we may well need to for that fairly simple network. Okay. The other combination type is where we get two or more in series that's in parallel with a third. Okay, and again, there is no real way, straight way to do that. How do you think we have to do that top one? If I label them R1, R2, R3, will I do the same with this one? How do we deal with that top one?
We work out the resistance in parallel. So we effectively have one resistance.
Yeah.
Then
So we do parallel on R1, sorry, R2, and parallel with R3. So we do that. That will give us R23. There's something I often call it. I think that's how I've done it in the notes. So that signifies the result of that. What you're effectively doing What about the second one then? Yeah, we add together these two. So we take them. Effectively, we can add those two together to give us R12. That's the result of that. And then what our circuit then is effectively is like this. R12 in parallel with R3, and we can then use either the product over sum or the to the power minus 1 formula to calculate. So we do a parallel on R12 in parallel with R3. Yeah. So that's how we do that. We break the circuit down into until we simplify it into. Eventually, we get to a stage where we got either parallel only or series only, and then we can find the total. All those resistors are 5 ohms. Where should we start with calculating the total? They're all 5 ohms. Oh, sorry, 10 ohms. Beg your pardon, well spotted. I was going to go 5 and I changed my mind. Right, all 10. So where do we start?
with R1.
Yeah, so we can go start with saying R12 is equal to R1 plus R2, 10 plus 10, 20 ohms. So we've turned that bit now, we can say that's 120 ohm resistor. Yep, so that bit is 20 ohms on its own. Where to next? Sorry?
The result from R1 and R2.
Yeah.
With R3.
Parallel that up with R3, yeah. So we'll be finding the resistance of R123. We're now going to find the resistance of all of that bit. Tell you what, let's do that in green. So we're now going to find the resistance of all that bit. We'll do that using product over sum. So it's going to be R12 times R3 over R12 plus R3. That's 20 times 10 over 20 plus 10 equals 6. Correctly rounded. I'd say 6 1/3 myself, but 6.7 correctly rounded. 6 1/3. A better way would probably be right 6 1/3, but we'll leave it at that. That's near enough. Ohms. So that's the total resistance of that whole part. It includes the R1, R2 and R3. Next bit. Yeah, we can do R5 and R6. We'll do that in red. So we're going to parallel those two up. Product over sum again. R5 times R6 over R5 plus R6. 10 times 10 over 20. Yeah, well spotted. I was just waiting to see whether anybody said that, that's all. Okay. Immediately really know that because there's two 10s in parallel, so we just go, that's 5, half it. Okay. So, what we've got now, because we've got the result of that bit, so that's 5 ohms. This middle bit we know is 10 ohms, and that bit over there is worth 6.7 ohms. So now we know we've got a circuit that we could draw. We could redraw our circuit. We've effectively reduced it to this. 6.7 ohms, 10 ohms, and 5 ohms. We've got an all-series circuit, and that's R123, that's R4, and that's R56. We've simplified it down to that, and we can now say RT is R123 plus R4 plus R56 equals 6.7 plus 10 plus 5 equals whatever that equals, 21.7, isn't it? 21.7 ohms. So although combination circuit could look initially quite complex, still only uses the same 3 formula options to break it down. So what you're looking for is little sections of it that are either all series or parallel that you can simplify into one resistor. What we're saying is, what resistor can we take those two R1 and 2 out, if put one resistor in its place and we still have the same circuit? And then the next bit was, well, we can take those two resistors out now and just put one 6.7 ohm in, we'd still have the same circuit. That's what you're doing effectively, using that step-by-step maths there. Okay, and there's some examples you have a go at in the second tutorial hour today. All right, with my help. How's that so far?